So we're very happy to have Kristan Jensen give us our next quantum space-time seminar on wormholes and black holes, black hole microstates and AdS CFT. Over to you, Kristan.
All right, thank you so much. And that was an authentic pronunciation of my last name. Usually we don't get to hear that over in North America. All right, so let's get into it today. This is a talk that is based on a number of papers that have been co-authored with Jordan Kotler, who's an excellent postdoc at Harvard. I've listed the archive numbers here. And well, let's get to it. I'm going to try to impersonate a chalk talk as best I can over the course of the next hour, with the intention of being, reasonably pedagogical, focusing on main points. So at any point, if you have any questions along the way, please feel free to chime in and ask. All right, so where we begin is with a very old observation that we all know, which is that black holes are thermodynamic objects characterized by an effective, by some mass, some temperature, some entropy, etc. And thermodynamic relations between those quantities. We've known this since the 70s. And there's an old question starting around then, which was whether or not one can give black hole thermodynamics a statistical mechanical interpretation. That is, whether or not one can account for black hole entropy in terms of microstates. So I can write this as, is there black hole statistical mechanics in addition to thermodynamics? And, of course, this is a question that's impossible to address within classical general relativity. The reason for this it's very simple. It's that the black hole entropy parametrically goes as 1 over g Newton, with g Newton being the weak coupling parameter of gr going to 0. And so from this entropy, one infers that if there is a microstate description, that the level spacings between adjacent microstates are parametrically order of e to the minus 1 over g Newton, which is non-perturbatively small in the Newton's constant. That's impossible to resolve using a classical GR computation. What GR gives you instead is what we would hope is a coarse-grained approximation to the actual density of states of some black hole. Coarse-grained over at least this resolution scale, e to the minus 1 over g. So for instance, if we take the equation of state that one extracts from classical GR and does an inverse Laplace transform to get the density of states, what you'll find is some smooth curve from a black hole, and something like a rho of E as a function of energy, which starts at some minimum energy and increases and is quite large, e to the order 1 over g. And what we'd like to think is that this comes from coarse graining over many such microstates. Of course, famously, we know more than classical GR. There are examples within string theory where this dream of finding a microstate description, we can actually achieve this, and one can enumerate the microstates of certain black holes. going back to Strominger and Vafa, and then more lovely recent work of Francesco Benini, Hristov, Zaffaroni, and then others following up on their efforts in the context of AdS black holes. Now, AdS CFT, I should, of course, that's sort of the, unfortunately, that's still the exception rather than the norm, that we can give a precise accounting of the microstates in terms of some dual description, but it's still a wonderful achievement. Now, AdS CFT relates this question of the microstate spectrum to a problem in conformal field theory. The black hole spectrum in that case corresponds to the spectrum of CFT states at energies above the threshold to make a black hole. So-called heavy CFT states. And to be less schematic about one example, but still schematic, we could talk about n equals 4 on the sphere. In which case there is some discrete spectrum of states. And the density of states, if we are able to compute it exactly, would, in the usual limits appropriate for discussing AdS CFT, would be separated into a bunch of different kinds of states. There's so-called light states with energies of order 1, states with energies of order root lambda, order n, corresponding respectively to supergravity modes, strings, and branes in AdS. And then there's also a slop of black hole microstates starting off at the threshold energy for a black hole, and all of those have energies of order n squared. And if we're talking about actual n equals 4, those states that spectrum of states is discrete, and we only get something continuous upon coarse graining, and that's what we see in gravity. But what's actually there is some very, 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 very fine delta Dirac comb with spacings of order e to the minus 1 over n squared. Now, and the present day, the precise details of that spectrum of heavy states, those are the black hole microstates in AdS 5 times S5. The details of that spectrum are beyond us. We don't know what those, the precise, quantum numbers of those states, whether they're energies and so on. However, despite the fact that we can't enumerate the quantum numbers of those states in detail, there is some universal feature that we ought to expect of the microstate spectrum that has been emphasized of late by Steve Shenker and friends, and comes to us from the quantum chaos community. And this universal feature is not the density of states itself or some coarse graining. It's in the so-called level statistics, that having to do with the differences between energy levels rather than the density of states itself. This is something that's a little bit different from what we're used to, but is just standard observable for that community. And the statement is that those people are interested in, among many other things, in the spectrum of a generic many-body Hamiltonian. So some Hamiltonian with many degrees of freedom. You can think of it as coming from a spin chain or some lattice approximation into a quantum field theory or what have you. And what happens in that case is that you get, a very complicated spectrum that's difficult to predict, but whose statistical features are well described by, well, in some cases by random matrix theory, and in some cases by some other simpler object. But the universal feature of level statistics that seems to be robust, seems to be true for just about any old many-body Hamiltonian, is that of eigenvalue repulsion. Which is essentially, the thing that we teach children in quantum mechanics, that, when you start learning about two-state systems and perturbation theory and so on, the statement that eigenvalues of a Hamiltonian don't want to lie on top of each other unless there's a symmetry that guarantees that they will. So usually they want to be away from each other, and the statistical properties of those level spacings are that they're away from each other and that there's some distribution for those. That is a robust feature for many Hamiltonians. And one way of, I'm not describing this in very precise detail. I can give a better picture for it now that gets at this. There's an object that people discuss in this context called the Lorentzian spectral form factor. Which in some ways is a more useful way to get at these robust features in the level statistics. There's some very fine-grained description in terms of the exact statistics of the distribution of energy eigenvalues, but it's kind of hard to, when you look at those formulas, to see, what do you then look for, say for n equals 4. The spectral form factor is in some ways a more convenient reorganization of the same data. And what is this? Let me write a formula what this thing is first. What it is it's trace, if you have some quantum mechanical system, e to the minus beta plus ith, trace e to the minus beta minus ith. This is like, two thermal partition functions, but with some real time evolution thrown in as well. And where the time evolution is, equal and opposite. One of these, it's going into the future, and one, it's going into the past. So, this is the canonical ensemble partition function at beta plus it and beta minus it. And what you get for this, for a generic Hamiltonian, is the following sort of plot. Let's call this whole thing z of beta t. So what you get is something that looks like, well, let me draw two curves. That's one curve. This is as a function of time t at fixed beta. That's not the curve that you get, but it's useful for me to draw so that I can correctly draw the actual curve that you get. The actual curve that you get kind of looks the same for most of the time, and then around here begins to oscillate wildly around the black curve. The blue curve is what you get for a single Hamiltonian. You get something that's fairly smooth, dips. It has these features that it starts off, if the time is small, this is basically the thermal partition function squared. And as time goes down, it decays, it dips down. This is the so-called, that early times, this is the dip. Then there's a second feature here where it grows for a while with large fluctuations that set in at times of order e to the entropy. This here is the so-called ramp. This is the so-called plateau. And the reason for those names is that if you do a little bit of either time averaging, do a rolling time average, or a little bit of ensemble averaging, a more radical thing to do, then either of those operations is sufficient to smooth out the wiggles, and you get a perfectly smooth curve for the spectral form factor. You get the black curve that I drew originally. And these features of eigenvalue repulsion are basically this one right here, this ramp region, and this plateau, where the thing levels off to a constant after a sufficient amount of time.
Yeah. Sorry, Kristan.
Go ahead, Sandeep.
Yeah. Can I ask you a question, please?
Oh, of course. Yeah.
No, thank you for that very, very clear introduction. But what I wanted to ask was, so this kind of a curve, I know one gets it, say, in the SYK model, at least the averaged version, say.
Right.
But is the statement that any generic system exhibiting quantum chaos will have such a curve? What's the statement more generally?
Well, the statement, there's not a, I mean, what has been done, there's been a tabulation. There's a taxonomy, if you will, of many different systems that folks in this community have been able to compute this quantity for.
Okay.
SYK is one example, but you can look at even billiard balls, classical chaotic systems, their quantum mechanical versions, okay. Spin chains. There's a plethora of examples that people have collated, and for each of those examples, the curve that you find for spectral form factor basically always looks like this.
I see. And so there's sorry, please go on. But there's some parameter like large n in these various examples, is it? And that separates the two regions, etc.
Yeah, what one needs is a large, and it's like in this quantity there's a temperature, an inverse temperature beta. What one needs is a large entropy. And that can be achieved through either a large n limit, through a thermodynamic limit, say if you have a spin chain, or those are the two common ways to achieve that. So yes, you do need some separation of scales in order for there to be this and this, but the parameter need not be large n necessarily. It can just be a normal thermodynamic limit.
Large entropy is enough, you say.
Yes.
Okay. And then just one more thing, which is, it seems very reasonable, but it's something I've been curious about, and I didn't know it had been looked at. But both the time averaging as well as a kind of ensemble averaging will smoothen out the jaggedness in the plateau region. It sounds reasonable. And then can you, in these examples, understand typically the time averaging as a kind of ensemble average?
No, I mean, this is how to say, I do not know of a reason why you should think of they seem to be two conceptually different things that are unrelated to each other. They're two different methods by which one can smooth out fluctuations, but they mean very different things. So for instance, when it comes to an ensemble average, what I wrote here is, trace times trace. The ensemble average would then be, you draw angled brackets around this thing. You ensemble average this quantity. Right. And this ramp and this plateau are visible in the connected parts of that average. However, if you just talk about a single instance, then you can think of that as some ensemble average where you just have a delta function in the space of Hamiltonians. Your distribution is just a single Hamiltonian. And the connected part of the ensemble average would be identically zero.
Yes, that's certainly true. But then you would do a
so
time. I thought the point was, where I'm going with this, but then it's an aside. You should please go on. We can even do this offline.
Sure. I mean, another way of saying it is that, it's sort of, you might No, I think it's an excellent question. It's something that we discussed a little bit in our paper, but only briefly. I mean, the point is that how to say, I mean, one way of saying the result is that if you have an ensemble average, if you have some connected part in this, that's not mimicking, you can't think of that as like a time average. If it's there in some connected observable, that's just different from taking a something that has no connected part and doing a bit of time averaging.
I see.
Sorry, Kristan, so just to ask that, to follow up on that, if I just give you the final answer, and I give it to you in some final averaged answer, and I give it to you in some detail, can you tell from the final answer whether it came from an ensemble average or a time average? Is there a smoking gun differentiation?
I need, the thing that one needs is you need to know whether or not, how to say, I would say the smoking gun is whether there's a connected part or not. So if you just hand me this quantity itself, that without giving me like the 1-point function, then I don't know.
Yeah, no, but Kristan, I guess, sorry to butt in there, but I think this is what Shiraz is also saying, and at least I had in mind was, of course, you're right that for a single instantiation, there isn't a kind of connected, there's a delta function there, there's no average. But if you just average out the time over some suitable interval, then do you more or less reproduce what you get from the ensemble? And where one is coming from?
Yes, the plot looks the same. The plot looks the same.
Right? So I mean, it's often the case in chaotic systems that, a time average, because the ergodicity means over some interval of time that a particular instantiation will still sample a lot of phase space. Right, in statistical mechanics, it's often the case that a time average can be reproduced by an ensemble average, right? So if the answer looks the same, isn't it plausible that that's what's going on? Sorry, Shiraz. Sorry, I just put some words there, but go ahead. Yes, but that's what I wanted to.
No, I mean this. To be honest, I mean, this is getting at the heart of where this talk is going. So I don't mind spending some extra time here talking about it. How to say? No, I would say this is what you just described are words that I would use when explaining to someone why these two things looking the same is a sort of a form of quantum mechanical ergodicity. This is the quantum mechanical version of a quantum mechanical version of that statement, of the classical statement. Now, the real question that I suspect that all of us have in mind here is, what does this mean? What's going on in gravity? Where we're going to be computing, where all this is going is to try to compute that from, I didn't know I could do that. Trying to compute that from gravity. And we find, in various instances, a smooth ramp. And the question is this coming, does the signal, okay, that's great physics. We shouldn't forget the physics, that is something very reasonable that we should expect for, the level statistics of n equals 4 or your favorite holographic conformal field theory. But what does it mean for gravity? Is there some ensemble averaging happening there or not? And the point that I would emphasize is that these wormhole computations that I'm going to describe, they're in the connected part. And it's a very simple observation, but that I don't know of a way of accounting. Like I would need a dictionary basically for a new form. Like there's a simple form of a holographic dictionary when you have multiple boundaries that would identify the connected parts of the connected geometries, their amplitudes, with a contribution to a connected average on the boundary, connected in the sense of ensemble average. And just because, you can draw spacetimes that are disconnected and spacetimes that are connected that would contribute to 1-point function and 2-point function of CFT partition function, respectively. And the question is, to my mind, is that we're getting at is there some alternative dictionary in which you could identify this as a time average instead? for a single instance. And I simply do not know. It really comes down to that. What's the dictionary by which we're relating the wormhole amplitude to something in CFT? Yeah. And maybe such a dictionary exists. I would be extremely interested if someone could tell me what that is. People have also proposed the possibility that maybe, you know, somehow gravity is averaging over what state you're in. Well, I would love to see a dictionary written down for that as well. But otherwise, it seems to me that you know, without that, then this really smells. I would say the connected things are a smoking gun signature of an ensemble average.
Okay. Okay. Thanks very much.
But we're getting there. So.
Sorry,
right.
could I button with a sort of simpler and stupider question? Could you please explain why the eigenvalue repulsion leads to the rise in the ramp? Is that
good? Let's see. So I don't know. I don't know how in a couple minutes to explain how you get a linear behavior. But what I can say is what this corresponds to, what this ramp corresponds to. Here's two ways of saying it. It corresponds, you know, it's easier actually to work backwards. The plateau corresponds to nearest neighbor repulsion, roughly. It's due to the underlying discreteness of the spectrum. And what happens in a generic system then is if adjacent levels repel, then that builds up and you have a long range repulsion between, you know, order one in the sense with respect to the entropy, but still many, many, many energy levels. And it's kind of a floppier repulsion. And its quantitative form is predicted by random matrix theory. It's encoded in a 2-point function of the density of states that goes like -1 over the dimension squared of the Hamiltonian. There's some double scale version of this that gives some finite answer that's suppressed in genus, but whatever. And it goes like E1 minus E2 squared. That's something that is repulsion. There's a minus sign in front, and it gets strong, and it's repulsion. It's going to, and this is becoming large and negative as the energies approach each other. So it's this feature. Then if you take this and if you convolve with factors of, use that Z of beta plus IT is integral over energies, density of states, E to the minus beta plus IT times the energy. If you use that together with that 2-point function and you look at the late time behavior of it, you see it grows linearly in time t.
Okay, thank you.
Yeah. Okay. Let's see. Well, so I'm 25 minutes in. To your talks, it's good that we're interactive, but how strongly should I try to be done by 11:30?
You can forget about that. If you finish by 12, that would be a surprise.
Okay. Okay, you set a challenge for us.
There's a time repulsion here. We go easily till 12, and you can go even longer. I think. Okay, well, I'm not going to abuse it because I will try to be done by 12, maybe a little sooner. Let's see. Okay, so so the focus of the rest of the talk is going to be trying to get at the spectral form factor, this 2-partition function object, from gravity, so from models of AdS CFT. And well, we're naturally dealing, since we have 2 partition functions, with a 2-boundary object in gravity, something ZZ. And we can obtain it, at least formally, by analytic continuation of a Euclidean problem, beta 1, beta 2, where we then analytically continue the inverse temperatures to be beta plus IT, beta minus IT. So what I'm going to do is I'm going to focus on,
the Euclidean two-boundary problem in quantum gravity. In particular, for regimes where one has thermal physics, there's a thermal circle. So if I want to discuss z of beta 1, z of beta 2 in gravity, perhaps with there being an ensemble average, trivial or not, I'm not going to assert that just yet, then the natural thing to to identify this with in gravity, following our nose, so to speak, would be to look at a two-boundary problem where, say we're dealing with n equals 4 on a sphere at inverse temperature beta 1, then we would study a two-boundary problem with two asymptotically AdS regions, or Euclidean AdS regions, where the boundaries are circle and circle, and then there's also, say, a three-sphere coming along for the ride. And then we would sum over all possible ways of filling in those asymptotically AdS regions. This would be anything. And, well, one way of doing this that we know very well is with the Euclidean black hole, or two copies of the Euclidean black hole anyway. And so, beta 1, beta 2. And, well, this contribution gives us the coarse-grained approximation to density of states, as I mentioned earlier. If you analytically continue it to real time in the sense required by spectral form factor, that is describing this. And the reason why it dips is basically the same reason why quasi-normal modes decay in real time when we study correlation functions in black holes. But that'll decay in time. And then, but it's big. That thing is order e to the n squared. So it's order e to the n squared times something that decays with time. And then, well, what we've done essentially, and what I'll be talking about, is to develop some technology to at least parameterize the next simplest geometry that one can write down, namely a wormhole geometry that kind of smoothly interpolates between those two regions. So beta 1, beta 2, sorry, and then there's
sorry to slow you down, but when I think of a quasi-normal mode in a Lorentzian black hole, I think of the reason for its decay as the wave going into the horizon. Are there words like that you can associate with the decay of the spectral form factor? What did you mean by this is the same reason as for the quasi-normal mode?
What did I mean as the same reason? It how to say, yeah, can I associate it with I think one can. I mean, it's a statement really about if you will, about the one loop determinants in front of the, if you approximate the Euclidean black hole amplitude as, e to the classical minus classical action times one loop determinant. It's a statement that the one loop determinant decays as you continue to real time t. And I don't recall the argument off the top of my head. I convinced myself of this at some point, but I don't recall. So let's, yeah.
Is it that one loop determinant basically is dominated by poles with these imaginary paths corresponding to the quasi-normal modes?
Sorry, yes, thank you, that's it. It's when you continue to real-time t, then it's dominated by those modes, they decay. And those eigenvalues, then how to say, you have to, there's some extra step you have to Fourier transform back from the frequency domain back to real time.
I see. Hmm.
And then it's essentially that, yeah, when you do that, then the fact that they're quasi-normal modes means that they're how to say, they lie in lower half plane by causality. And so as you continue to real time t, then those things will exponentially decay as time goes on.
I see, but there isn't a nice Lorentzian picture where you see something decay, like you do for the quasi-normal modes.
Yeah, I think it's coming from the spec. You can write that one loop determinant in terms of the spectrum of quasi-normal modes.
Okay, fine, thank you.
Yeah. Okay, good. We can reconstruct that. Okay, so what we're getting at is the wormhole, and the claim here is that this computes something else that's has a nice, you know, oh, my screen is out of sync.
Sorry, just one quick follow. So is the time scale of decay in the decay phase set by the lowest quasi-normal mode? Is that true or not? Is it exponential and set by the lowest quasi-normal mode? What about the fluid dynamical quasi-normal modes, for instance? They're very light.
Yeah. No, it's a good question. I don't know off the top of my head. I admit to my brain, part of my brain is trying to figure out how to get the screen working again. I think I need to stop sharing
sorry
and to reshare.
Yes.
Yeah, let's see if it. Let me share. Let's see.
Yeah, while Kristan is doing it, I guess, Shiraz, your point is the fluid hydrodynamic modes will go down to zero frequency, yeah? So your point is...
there we go. Yeah.
At least on RD. Maybe the sphere cuts it off, but I was just wondering whether we could get the time scales from that. Yeah. Anyway, I think Kristan should, yeah.
Yeah, it's a good question. I haven't actually thought about it carefully, so I should not give an answer. My intuition would be the same as yours, but I should think about it before what. Yeah, it's really a question about this, you know, this one loop determinant and convolving to the real time domain. So it's pretty simple to just write down some formulas and see what you get. But I don't trust myself to do it in real time in a talk, so I will stop there. What we focus on, so that there's the black hole part, and then there's the next thing that we can write down. The next simplest thing that we can parameterize is a wormhole, which we've been able to make some progress on. And the claim is that this computes another coarse-grained quantity, just like the Euclidean black hole amplitude does. It gives the coarse-grained approximation to these level statistics, in particular to this long-range repulsion. I'm writing it this way, you know, this is the result that we're going to build up to, but so that there's a nice parallel between the old Euclidean black hole thermodynamics story and kind of the wormhole story. It's related to a similar property of the microstate spectrum. So that's what we want to get up to. What has actually been computed? When it comes to these wormhole amplitudes, well, wormholes have been computed in JT gravity by Saad, Shenker, Stanford in 2019, and then also in variants thereof. That's a horrible way of writing thereof. So for instance, by Stanford Witten, who looked at, for instance, supersymmetric variants of the of JT gravity, and also by Maxfield, Turiachi, and Witten. Both of those in 20, this in 19, in the context of JT gravity with defects. And no, those cases, you know, two-dimensional models of dilaton gravity. It is also, well, sort of the simplest wormhole amplitude has also been computed in pure 3D gravity with negative cosmological constant. The amplitude I have, you know, in JT is so nice that you can just, you know, compute anything that you want, at least the amplitude over space-time of fixed genus. In 3D gravity, it's a bit harder, much less is known. What has been computed is a particular wormhole amplitude, and only one has been computed to my knowledge. And it was something that Jordan and I did last year. So torus times interval has been computed. So the thing that looks like a torus and smoothly interpolates to a torus on the other side. That was computed by us last year. And then when it comes to, you know, more than 3 dimensions, relatively little is known. You know, in 2 and 3 dimensions, those models are essentially, you know, they're quasi-topological. There's boundary degrees of freedom, there's moduli, but there's, you know, no propagating degrees of freedom in the bulk. So in those cases, in fact, the wormhole amplitudes have not just been, you know, computed, they've been exactly, they haven't been approximated, they've been exactly computed. In more than 3 dimensions, what has been done is to kind of parameterize the wormhole amplitude as best one can, and there's loop corrections and so on that are presently unknown. And that was also something done by Jordan and myself in 2 papers, one at the end of last year and one this past April. And that was, and the same methods allow you to tackle wormholes, not just in Einstein gravity, but in supergravity and, you know, all the things that we're used to from string theory. Freund-Rubin compactifications and so on. So as I said in words, these 2 things have been computed exactly. And this has really been parameterized, has a number of features. It's cannot be computed exactly anyway because it's UV sensitive. The loops, as I said, are presently unknown. Although there is one thing that we'll get to at the end, which is that in higher dimensions, the whole wormhole amplitude is not known, but the wormhole amplitude admits an integral transform. Which does have a saddle point approximation, and where the saddle point is the so-called double cone geometry of Saad, Shenker, and Stanford again, but this time a paper that they wrote in 2018 rather than the one that solved JT gravity in 2019. Now, the thing that's non-trivial about all of these computations, and you know, the reason why they had not been done before, is that all of the wormhole amplitudes I just described do not admit a saddle point approximation. So, you know, it's a fully off-shell instanton-like problem in gravity. It's a non-perturbative correction, something like an instanton, but without a saddle point approximation. So you really have to roll up your sleeves. And it's actually quite important for, you know, everything that we know about AdS CFT to be true, that these things do not have a saddle point approximation. If there was, you know, some wormhole, Euclidean wormhole, that had a saddle point that was the saddle point of Einstein gravity or what have you, then you could Wick rotate. You know, say if that wormhole was time translation invariant, And if you Wick rotated, you would get a Lorentzian wormhole, which was traversable. But without any interactions between the two boundaries. And that would violate, well, for instance, boundary causality. You would get, for instance, that operators on one boundary don't commute with those on the other, even though there's no interactions between the boundaries. So that's bad. It's very, that would be very bad if that happened, but it doesn't because there's no saddle point approximation to this. So there's no, we don't find any classical, any solutions to Einstein gravity of this sort. However, if we just ask about the sum over metrics, talk about the amplitude, which would get a contribution from only, off-shell configurations, well, there's no reason why that has to be 0. And what has been done is to compute it in these simple models of low dimensional gravity, and then to efficiently parameterize that amplitude in the thing that we're actually interested in higher dimensional Einstein gravity and supergravity. I should write down the answers for what you get in 2 and 3 dimensions because they are so nice. In JT, what you find is that the amplitude of the simplest wormhole, something that has the topology of circle times interval and depends on 2 boundary temperatures, something very nice. It's 1 over 2 pi square root beta 1 beta 2 over beta 1 plus beta 2. JT gravity has a genus expansion with a genus counting parameter, e to the s naught, which is very, very large. You can think of s naught as the extreme mole entropy of a black hole in the model. And if you, the cylinder has genus 0, has a rather Euler characteristic 0. And so this thing doesn't depend on that parameter. In contrast, the disk amplitude, having Euler characteristic 1, does, and it goes as 1 over beta to the 3 halves e to the s naught plus 1 over beta. For the disk, this would be the analog of the Euclidean black hole here. It is much, much larger than the wormhole. However, if you analytically continue to real time, disk squared becomes smaller than the wormhole after a sufficient amount of real time evolution. Okay, that's what one finds in JT. In AdS 3 gravity, so this was myself and Jordan, what has been computed is the torus times interval amplitude. This, the kind of geometries again they look like this: torus on one boundary, torus on another. So they're characterized by independent complex structures on the 2 boundaries rather than just inverse temperatures.
Sorry, Kristan, sorry, can I just ask you one quick question?
Of course.
Yeah, I did look at your papers, but now I'm not recalling them clearly enough. So here you worked with just the Chern-Simons theory, is that correct? Or when you say AdS 3,
so I mean pure 3D gravity, and what we did, what we did was we worked in the first order formulation of 3-dimensional gravity, which looks like Chern-Simons, but it's not. There's some subtle difference that I can mention later between what you would have found in a Chern-Simons version of the computation that we did and what one does from a sum over first order variables.
I see. Okay.
Yeah, basically,
So
if one
you
had
worked
done this computation in Chern-Simons theory, you would have gotten infinity, whereas in gravity, you get some finite answer.
I see. Interesting. Okay. But so you worked directly with the Feuerbine and the spin connection, etc., and worked with the theory. Okay. Okay. Thank you.
Yeah, that's right. It's a subtle computation. It's this would be the subject of a talk in and of itself if we.
Yeah.
So okay.
Kristan,
Yeah.
can I ask you a question?
What one? Of course.
Related to Sandeep's question, it's a follow-up of that. So in Chern-Simons theory, if you were to do this, you would get contribution to the partition function, presumably from all the modules of the WZW model.
Yes.
Right? The vacuum module and the other representations as well.
I have to say,
you entangled contribution like that.
Yeah, if you did this in Chern-Simons, that's right. You would interpret this as a WZW partition function, which would just be a sum over characters of all the integrable representations of the WZW.
Right. But
the thing is that.
Sorry, go ahead.
Oh, I was going to say something that happens in that would happen in Chern-Simons, though, is that there is a zero mode that appears that's kind of important. You know, it would be the volume roughly of the gauge group.
Mm-hmm.
And that volume, you know, if you're doing SL, so there's some sort of similar resemblance between gravity and first order variables and a non-compact Chern-Simons theory, SL2. And so that's the reason why I said that if you evaluated this amplitude in Chern-Simons theory, why you would get infinity is because the whole thing is proportional to volume of the gauge group.
I see. So in gravity,
cool.
Would you get of tau 1 of tau 2, just like in what you would expect in WZW model partition function?
Sorry, the first part of your question cut out.
No, so in gravity, if you were to do the same calculation, which you do you get sums of products of functions of tau 1 and tau 2?
Yes.
And
exactly.
Is there any interpretation in terms of these semands?
Yes. Yeah. So okay. So the let me write the answer, and then I can write it in the way that you're suggesting.
Thank you.
But the answer is this is great. Sorry, the connection is breaking up. So I'm just going to write the formula, and then I'm going to write it in some second form where one has, how to say, this.
We can't hear you, Abhijit. I'm not sure it's your connection or mine. Or...
No, I'm muted myself.
No, I can't hear it.
No, I'm yeah, Kristan, we cannot hear you.
Can you hear? I wasn't talking. Abhijit, can we?
Yeah, I can hear Kristan well. Abhijit, I suspect it's your end. That's the...
No, but I wasn't talking either.
Oh,
okay.
But there was a delayed. Your conversation was coming delayed.
Oh, sorry about that.
No.
Yeah, this was the thing that I was after.
Yeah. So exactly. So the chi's here are normal Virasoro, non-degenerate Virasoro characters. And what you get is a structure where, if you interpreted this as coming from states, where the states look like ordinary representations of Virasoro on each boundary, with a uniform density of states. But then there's an overall factor. What I've written here is V naught, that's analogous to the thing that you would have gotten in Chern-Simons, the volume of the gauge group. In gravity, it is instead, it's some finite thing. It's related to zero modes that are translations of one boundary relative to the other. There's some exact zero modes in 3D gravity of the sort that kind of twist one boundary relative to the other. And that volume goes as square root m tau 1, m tau 2. If the two inverse temperatures were the same, then it's just, the amount of inverse temperature times some number, times some finite number. And how to say, but yeah, this is what you would find. And then there's a Maloney-Witten like sum on top of this, because you can have wormholes where modular invariance in CFT is a kind of dumb statement. It's just the statement that there's infinitely many ways to parameterize the same torus. And there in gravity, that if you have the same boundary torus, then roughly speaking, this implies that you have to sum over all possible, there's kind of a linking between the cycles in this geometry of the torus on one boundary with those on the other. And that can be done in any way where like A gets identified with A, B with B, or A with B and B with A, and certainly many other choices. And that corresponds to this sum over SL2. But the individual object, the summand here is analogous to a WZ.
Sorry, my internet is not well. I think I missed what the H was. What was the domain of integration of H and H bar?
Good. The domain of integration, if you track it, ends up being exactly from C-1 to infinity for both.
Okay, thank you.
Yeah, these are all heavy states. And go ahead, Sandeep.
Sorry, no, you must go on, but just thanks for this. So the point is that in gravity you get a finite answer, but in the Chern-Simons theory you would get V naught to be the infinite volume of SL2R. Is that the difference?
That is one of the points of this. That's right. Yeah. Okay. The Abjit was wanting to see there's some spectral representation of this amplitude that you would have guessed on that. If we were dealing with Chern-Simons, there's a well-known formula for this thing, and there's some spectral decomposition for this amplitude. And in 3D gravity, you have something that looks very, very similar, but it differs in a couple of crucial ways. One, that it's not infinity; it's some finite, well-defined thing. And second, to me, this matters a lot because that particular prefactor is very important if you try to then compute Lorentzian spectral form factor from either in JT gravity or from this three-dimensional result that I flashed. Then, if you continue to real time in the way that I said you do to talk about spectral form factor, and in 3D, you have to look at, if you want to look at the natural definition for the spectral form factor is when you've kind of accounted for states that are related to each other by symmetry. And in 3D gravity, where there's 2D conformal symmetry on the boundary, that means that you should look at primaries of fixed spin. So if you kind of strip off descendants from this amplitude and then work at fixed spin, and you look at the spectral form factor, it's exactly what you would have predicted from a random matrix theory ansatz. Or at least the ramp is. You get a ramp, you get a ramp in the Lorentzian spectral form factor exactly predicted by random matrix theory. And when I say exactly, I mean there's a number, there's a coefficient that one gets. So z beta t has to go like 1 or t over 4 pi beta plus fluctuations that are non-universal in random matrix theory. This is what you get from this is what you get on the nose from the 3D gravity computation as well as from JT, including the 4 and the pi.
I see, I see. And just very quickly, the random matrix theory is the same one that Saad, Shenker, Stanford looked at, that is Hermitian matrices in the appropriate double scaling limit. Is that right then?
Right. Although I have to say that this thing about the ramp is much more universal than how to say. If you say you're working with a random matrix theory, so some double scaled one Hermitian matrix model, so large Hermitian matrices, that's not enough to specify the model. And basically, there's an arbitrary potential sitting there, or you can think of it as the leading density of states is some input parameter. Depends on the details of the model. This thing that I'm discussing, the ramp, this is actually universal across all of double-scaled one Hermitian matrix, random matrix theories. So the density of states, in other words, depends on the details of the model, but this feature of the level statistics is completely universal within the symmetry class.
I see. Okay. Yeah. Okay. Yeah. The endpoint correlators probably depend on more than just the double scale.
Yeah. So what is meant by the Saad, Shenker, Stanford matrix model is a very particular, if you will, distribution of matrices. To be more okay. So if you say you have a Hermitian matrix H, then the ensemble average in some matrix model is, something of this form.
Yes.
And there's, you have to specify the potential, the distribution. And that's something that Saad, Shenker, Stanford are able to do indirectly. But there are some universal features of these random matrix theories that hold independent of the details of that potential. And those are exactly the ones that we might hope are reproduced in gravity.
Okay, thank you so much. Please go.
Yeah. Okay, so that's the lower dimensional story. Of course, that's very interesting to some of us, but it's not also the reason, or how to say, when I started off learning about AdS CFT, it was about n equals 4 and 10-dimensional strings and supergravity and so on. What's the status there? Rather than, we retreated to low dimensional gravity in order to learn features that would be useful for teaching us about higher dimensional physics. Well, what does this teach us about the problem we originally wanted to solve? What about AdS 5 times S5, etc.? And the short answer is that that's a hard problem. And it's hard for the same reason that I mentioned before, namely that these wormhole amplitudes are non-perturbative corrections without a saddle point approximation. And you can actually prove that particular statement. There's something called the Witten-Yau theorem. which, among other things, implies that there are no Euclidean wormhole solutions to Einstein gravity with positively curved boundaries, or with zero curvature on the boundaries. So that would forbid, for instance, wormholes connecting, solutions to Einstein's equations whose boundaries are circle n times sphere. That thing, you would not find a saddle of that sort. It is worth noting, there are saddles where the boundary is negatively curved. So for instance, where the boundary is hyperbolic space or some quotient of it, those, so negatively curved boundaries, you can get those, in fact, just from orbifolds of empty AdS. Those don't seem to have any connection to the black hole physics, and they're also generically unstable within supergravity, at least, once you uplift those to configurations in supergravity to various instabilities. Usually brane nucleation is the most common one. But if you have positively curved boundaries, in particular if there's thermal circles and some positively curved space left over, then there are no solutions to the Einstein field equations of this sort. So you need some more tools to proceed if you're not going to give up. And what we did in these papers I mentioned was to develop some tools to tackle these amplitudes, kind of inspired by how the guts of the low dimensional computations work. And these tools, I could talk about these for a long time. I could probably give a talk or two talks just about the tools. Unfortunately, I won't. But let me summarize them in brief. The sort of two parallel tools that we have developed or adapted to the problem at hand. The first is the method of constrained instantons, which existed before us, but which we adapted to gravity in kind of an obvious way. What are constrained instantons? Well, they're something that's known in quantum field theory in examples where there's no instantons, but there are instanton-like corrections to amplitudes. So for the canonical example of this is Yang-Mills in a Higgs phase, 40 Yang-Mills in a Higgs phase. In that case, one can prove there are no finite action instanton solutions to the field equations because of the Higgs vev. But there are still instanton-like corrections, for instance, signified in non-Borel summable in terms of growth in perturbative amplitudes. So there are instanton-like physics, but there's no instanton solutions per se. What you get instead is if you sort of foliate your field space of integration by some constraints, you work at some fixed constraints. Go ahead, Sandeep.
Sorry, the internet, but just to make sure. So if you take pure Yang-Mills theory, say in 3+1 dimensions, without any matter, then you do have instantons, right?
That's right.
But when your statement that you didn't and you needed constrained instantons, that's when you start adding matter, is it? Or
yeah, for instance,
I didn't quite.
Yeah, that's when you have matter. Yeah. So for instance, if you have SQCD with NF equals n-1 flavors, that's the canonical example. So think SU2 super QCD with one quark. Then if you're out on the moduli space of that vacua for that theory, SU2 is broken, and there are no instanton solutions anymore, owing to the Higgs vev. Did the talk get, sorry, The internet is...
I can hear you.
Okay. Sandeep, did you hear my answer?
No, I'm really sorry, but you said take SQCD and say NF equals N minus 1, and that's the case where...
That's a canonical example.
And I know this is the famous Seiberg case where, you know, you lift the moduli space with a runaway behavior, but even if you gave masses to the flavors, is it you don't have these instantons, and you need constrained, is it?
Yeah, you need the constrained instantons. Even, yeah, that's right.
Okay.
As long as you have, that's right. Yeah, so that method can be adapted to gravity. In order to proceed, one needs kind of a inspired choice of constraint to proceed effectively. There's a second set of tools that we developed that apply in gauge theories, which I haven't seen before. As far as I know, they're new to us, which we dubbed lambda solutions. And, you know, we have two kind of ways of discussing the wormhole amplitudes in terms of constrained instantons or these lambda solutions, and the results are equivalent. Let me, for the purpose of this talk, briefly say what the lambda solution corresponds to. If we want to deal with summing over metrics in Einstein gravity, gravity is a gauge theory. We divide by diffeomorphisms. And so we got to gauge fix. My test of the internet is basically whether or not I can see Sandeep's face, and he got frozen. Shiraz, can you still hear me, or?
I can hear you perfectly. Let me put my video on as well, so you have another.
Okay, good. Okay, so I guess the problem was on Sandeep's end. Okay, so
I'm terribly sorry. I'm back now on a different internet provider. Let's keep our fingers crossed. I apologize. Please go ahead.
Yeah. Okay, so something we can do if we're dealing with AdS is to performing a gauge fixing analogous to Pfefferman-Graham gauge, where we fix the metric, the line element rather, to have this kind of form, where we separate out one coordinate from the others. I'm going to call it rho. Rho is going to be a radial coordinate, and x are going to be the boundary coordinates, like field theory coordinates. So the picture I have for my wormholes that I'm going to find this way are that here's the xi, and here's rho. And in other words, we gauge fix rho component of the metric to be 1, and the mixed components rho I to be 0. Mm-hmm. Well, you do this, then the action that you're dealing with has, not including ghosts, so just the bosonic part, as the usual Einstein-Hilbert cosmological constant terms. And then there's the gauge fixing term, which would fix those components of the metric. And the kind of obvious dumb statement here is that the only degrees of freedom left in the gauge fix theory after enforcing the constraint are the Gij. Not rho or rho I. And or equivalently, the gauge fixing auxiliary fields lead to some right-hand side of Einstein's equations. Basic result. This lambda solution story, we call them lambda solutions because lambda is this gauge fixing auxiliary field. And usually it's a Lagrange multiplier, and usually we call Lagrange multipliers lambda. Is that there are new solutions to the equations of motion of the gauge fix theory that are not solutions to all the field equations, to all the field equations, but they are solutions to the equations of motion after imposing the gauge constraint.
It sounds very much, Christian, like the constraint equations you would get. This is like an ADM kind of gauge fixing, isn't it? You've set the analog lapse to 1. It sounds very much like you're not imposing those constraint equations from the shift and lapse, and then you're getting a solution. Is it something like that?
How to say? Okay, so ADM formulation is different from standard. It's a Hamiltonian formulation of gravity where you integrate in fields, and then you find that lapse and shift are Lagrange multipliers. They enforce constraints. So it's a different thing than what we're doing. Indeed, if that was what we were doing, if we were ignoring some of the constraints, that would have been how to say, that would be illegal. But if we are, what I'm describing is purely within the second order formalism without integrating in the canonical momenta, so that you're doing ADM. Now, that being said, the geometries that we find by this do have some kind of like if you thought of them in ADM language, what do they look like? They look like Hamiltonian equals constant geometries, if you think of rho as generating kind of time evolution. But I stress that how to say, I think that's an accidental. I'm not sure that's a meaningful statement. It's kind of like if you tried to process the geometries that way, that's what it would look like. But I think the geometries I'm describing only make sense in this gauge fix second order formalism.
Yeah. No, I just meant the limited point that with the Lagrange multiplier, the equations of motion for the components of the metric which appear in the Lagrange multiplier will change, right? They'll be proportional to your Lagrange multiplier.
Right.
And
that's right. That's right.
Okay.
That's the point. Yeah.
Okay. Anyway, yeah.
Yeah. So it's analogous. These are analogous to we're used to in classical mechanics that if you have constraints, then you can have solutions where there's a constraint force and ones where there's not. And the analog here is you can think of these wormhole geometries as solutions to the field equations where there's a constraint force coming from the gauge fixing apparatus.
Right.
And I haven't seen this before, so I'm naturally distrustful of new things. But I don't see a reason why, following the rules of field theory, I shouldn't be allowed to do this. In particular, one thing that we checked was if we go back to pure electromagnetism, is this what you do in electromagnetism or not? Well, it's certainly what you do when you start evaluating loop contributions to amplitudes. You sum over everything weighted, including the gauge fixing apparatus, of course. It is not the case there that there are new saddles to the field equations that come from this and any of the standard gauges. So I at least in electromagnetism, there's no contradiction with anything that I know there. In Yang-Mills, I'd say it's not known at this point, but basically, this seems perfectly legal to me, and it's just what you have to do quantum mechanically in a gauge theory when you gauge fix, and this is what we find. So let me write down an example of the sort of solution that we find this way. What I'm going to write down here is a wormhole, which is topologically S1 times S3 times an interval, where the interval is the radial direction, and S1 times S3 are all in the boundary. So this would be relevant for, this is the kind of geometry you find on the boundary of the AdS5 black hole. So It's some expression where tau is Euclidean time and periodic with periodicity 1. And if you stare at this line element for long enough, you know, this is the solution, if you will, to the ij components of Einstein's equations. You know, rho and rho I are not fields in the gauge fixed theory. So we don't vary with respect to those. And correspondingly, this thing is not a solution to the rho component of Einstein's equations. It has some features. It's a wormhole, so it looks like that roughly, where there's a bottleneck whose volume is labeled by a parameter b, roughly b to the 4 at the bottleneck. And the way that beta 1 and beta 2 appear here are such that the two boundaries are achieved as rho goes to plus and minus infinity. And over here, there's a circle size beta 1. Here, there's a circle size beta 2, physical size. And this parameter b, if we want this geometry to be non-singular everywhere, including at the middle, is bounded below. It has to be bigger than 1, the way that I've parameterized things. And any such b will do. So there's a family of these geometries. So a few comments about that. That's the first. We get a family of wormholes this way. All the ones that I've written here have spin equals 0. They're labeled by B. Second comment about these is that this geometry, it's not at all obvious, but it's the analytic continuation of the usual Euclidean black hole in AdS 5. In particular, if you substitute in beta 1 is minus beta 2 is beta. This is the standard AdS 5 black hole, but written in different coordinates than how it usually is. And this b parameter then is the mass of the black hole. There's some relation. B squared times b squared minus 4 is proportional to the mass in that case. And so, you know, it's really the Euclidean black hole only then if you fix b in terms of beta in such a way that there's no conical deficit. And if you look, well, yeah. And if you look at this, you can see, okay, if beta 1 is minus beta 2, then how can this be some standard Euclidean cigar? Well, this thing will shrink off to 0 at rho equals 0.
I see.
The third, oh, go ahead.
No, I was confused about your comment number 2. This has two asymptotic boundaries, right? So when you say it's analytic continuation, you mean of one of these thermophile double type of black holes, or?
What I mean, let's see. What I mean is that if I take this geometry and I let beta 1 equal minus beta 2, then the geometry, what it looks like is, what it really looks like then, this thermal circle shrinks, it degenerates in the bulk. Okay. And so what you get then is some geometry that looks like this, where you have these two kinds of things that meet at a tip at rho equals 0. And I'm saying, if you take half of that, that's the Euclidean black hole.
Okay, I see. Got it. And I guess then for that case where beta 1 equals minus beta 2, all the remaining equations of motion are also met, I imagine. Huh?
That's right. That's right.
Thank you.
And the third comment is that if you look at these geometries, they have a very simple form for the renormalized action. You know, there's an old result in GR that if you have an isometry then the action of that geometry of gravity evaluated on that geometry is going to go like the size of that circle times the conjugate charge, so beta E. Well, the wormhole has kind of the next thing. There's two asymptotic circles, and the normalized action goes as it's finite, and it goes like beta 1 plus beta 2 times the energy. You can think of this as beta 1 E1 plus beta 2 E2, where the two energies are the same, and that's like a gravitational Gauss's law, relating energy on one boundary to energy on the other. And the energy is, it's roughly this quantity b to the 4 over g Newton. So it's, if b is 1, if this wormhole is macroscopic, large order 1, so macroscopic wormhole, then this energy is very, very large, order 1 over g Newton. There's a question. I see a raised hand.
Hi, yeah, Kristan, hello.
Hello.
Yeah, I just wanted to know the role of ghosts in your action formulation and the effect of counter terms if you're doing this on AdS. Like, it seems a bit obscure to me. Like, I got the gauge fixing part, I guess, but like, where did the ghost part of the action go? Does it have any effect on these results? And are there any counter term and boundary effects which we have to be, like, to what extent are these results sensitive to that?
Right. So yeah, let's see. So I'm just presenting the bosonic part of the story because I'm interested in finding like the analog of saddle points to expand around. And then, I would look at all fluctuations around these things, bosonic fluctuations, ghosts, and so on. The thing that would be very important in the ghost sector that would kind of render all of this meaningless is if there was some ghost zero mode around these geometries. But that, sort of, you can reason quickly that there are no such ghost zero modes in this case. That would correspond to, basically, residual, some unfixed gauge redundancies in this background that one has to kind of deal with by hand. So the ghost, basically, the net effect of the ghost is to give some overall determinant on top of the bosonic amplitude, the integral over bosonic fluctuations.
Okay, thank you.
Now, I should mention, if we were dealing with a different problem, for instance, if we were dealing with a problem in supergravity, where the boundary conditions were those appropriate for computing a supersymmetric quantity like the index, then there would be more fermions than just the gauge fixing ghosts. There would also be, the gravitino and so on. And in that case, how to say, there's going to be a very interesting work coming out very soon by Luca Iliescu, Joaquin Turiachi, and cannot remember the third collaborator's name, where they're going to show that generically then there's not a ghost zero mode, but a gravitino zero mode, so that these wormhole contributions are identically zero.
Kristan, if you changed your gauge fixing condition infinitesimally, you made a small change in the gauge fixing condition, is the existence of these saddle points sort of stable to that change? And does the action, and the action for the saddle points is invariant under this change?
Well, okay. Is the action invariant? So what happens is that there's a family of these wormholes, as I mentioned. And so let me answer your question this way. Let me say that one, that the existence of the wormholes is stable with respect to changing the gauge fixing condition. The second thing, that what you were saying about the action being the same, I think that is true, but the wormhole changes a little bit. So if you change the gauge fixing condition, I can't prove this statement. We've just noticed it empirically by doing so, basically changing as we can in the space of gauge constraints around the radial gauge. What we notice is that the wormhole geometry changes by a little bit, but that there's always a wormhole that has this action, that effectively has this energy with energies in the same range as what I've written here. And I guess I should also say that this range of energies that we find coincides with the range of energies of black holes.
So in the case of AdS 5 plus S5, that would be 0 to infinity?
Yeah, it's from the small black hole threshold on up.
Which we don't really know. I mean, it's just in units of n squared, it would be 0.
Yeah, that's right.
Okay.
Well, yeah, I mean, there's in AdS 5 times S5, there's the whole business with the Casimir energy and so on. And there's some ambiguity in where the spectrum of black holes begins. And
but the same energy as the vacuum, basically, to order n squared, right?
yes, that's right.
Okay, thank you.
So what you get out of this then is you get the net output from this analysis is a useful parameterization of the wormhole amplitude. Where it looks like an integral over, we can write there's an integral over B, there's a family of these configurations, and one can trade that for an integral over this energy E, which runs over basically the range of B so that the wormhole is non-singular. You can translate that into an integral over the range of energies of Euclidean black holes. And then there's an E to the minus S, which is what I wrote there, times, and then there's a loop expansion around these wormholes, provided that the wormhole is macroscopic. That is, provided we're away from the limit where the bottleneck is pinching off to 0 size. And well, it'd be a 1 loop factor, which we cannot compute. There's 2 loop corrections and higher that we cannot compute, and so on. What we get is a parameterization of the amplitude. And this parameterization is useful. It teaches us one thing immediately. We'll see it's more useful shortly, but one immediate lesson that we get from it is that there is no saddle point in this integration variable E that remains. These geometries were, if you will, saddles of the gauge fix theory, but then there's this residual integral over E. Well, there's no saddle point in E. There's a Boltzmann-like suppression here, which wants the energy to be minimized. The wormhole basically wants to pinch off. And that's the region of integration that dominates the amplitude. That's the sense in which the whole amplitude is very UV sensitive. Good.
Sorry, Kristan, a very stupid question, please. Excuse me. What you said is that you've got a family of wormhole solutions, and the action of the solution depends on the parameter in this family. Is this right?
Yeah, it depends on this parameter. Yeah.
That almost sounds to me like a contradiction in terms, since a solution extremizes the action. Right.
Yeah, that's right. So what happens is, how to say, it's a very annoying case where how to say, let me phrase it this way. This parameter B acts, if you change it by a little bit, it's a non-normalizable fluctuation of the metric. It goes all the way out to the boundary. But it does so in such a way without changing the conformal class of the boundary metric. It's like an overall rescaling of the boundary metric. So it's something that we really do integrate over, but it's a non-normalizable fluctuation. So the usual thing, the statement that if you have a saddle point, that it's an extremum of the action, well, that depends, that your fluctuations die off or appropriately at the boundary. You can have, right? there's a boundary term in the variation of the action.
Yeah.
And so this is a case where you just pick up that boundary term, but and normally that's how to say, that would be a sign that you have an inconsistent variational principle or so on. But in this case, we know what the right boundary conditions are. We integrate, I mean, let me flash the metric again. We integrate over, you know, things that hold the conformal class of the boundary metric fixed. And what this B does is it just rescales the boundary metric by a little bit. And that's something that it's not fixed by a boundary condition.
Okay, so it's very unusual.
You know, there's a
it's unusual.
Yeah, sorry, no, but I just wanted to say there's an exact parallel, I think, in JT gravity also, where this is an analogous, you know, parameter, which is like the modular parameter you'd associate with the double trumpet, for example.
Yes.
Right? And
yeah, that's exactly the same. That's right.
Yeah, and so it's a little bit like a modular, Shiraz. You know, if you have this double trumpet kind of geometry, let's say you know, you have the cylinder-like thing. If you normalize the length to be 1, then the size of the neck becomes, you know, the size of the circle in units where the length is 1 becomes a parameter, right? I mean, that's like
oh, I see what you're saying.
Yeah. And Christian, I'm just saying this, you should go on, but I mean, you know, with matter, we have the same issue we are struggling with in JD gravity, that again, you have this divergence where B goes to 0 and it's very UV sensitive, etc.
Right.
But anyway, I'll chat with you offline about that, because
I should have said that. Thank you for reminding me. Yeah, and anything other than the simplest kind of topological models. I mean, you expect on general grounds there to be divergences, UV sensitivity there. From that's a general thing you would expect if you have propagating degrees of freedom there, in addition to everything else, including, and you know, in 2D and 3D gravity, there's no propagating degrees of freedom in the metric. But you would see that if you have matter coupled to JT, because in the limit where the wormhole is pinching off, you have a small circle. And if you look at quantum degrees of freedom around the small circle, that will give a divergence as B goes to 0, as that size goes to 0. And in higher dimensional gravity, you know, you don't need to couple the matter. There's propagating modes in the metric itself. So,
yeah, that's exactly what I was going to say. Right. Exactly.
Yeah. Okay, so at this point in the talk, we've parameterized the wormhole amplitude, but in some way where we learn it's completely UV sensitive, and it seems that nothing more can be done with it. Fortunately, life is not that. We can get more mileage out of this, but just let me do so in a few minutes. I want to take stock of what we've learned so far first, just because there's a lot of parts to this talk. So taking stock so far, you know, if we're interested in the 2-boundary problem, we know of 2 configurations so far: the Euclidean black hole squared, 2 copies of that. There we go. That looked awful. So this is 2 copies of the black hole. There's the wormhole. It's UV sensitive. There's all sorts of other topologies which we know nothing about at this stage. And you know, so far I discussed these wormholes in the context of Einstein gravity, but you know, you might wonder, well, what about full-fledged AdS CFT, like AdS 5 times S5? What about the full thing? Another question that I have not discussed at all is, you know, just are these things stable configurations in Euclidean gravity or not? What about stability?
Sorry, a quick question, Jens. The E goes to infinity wormhole that seems to dominate, is that the one with 0 neck size or infinite?
Sorry, the thing that dominates is the one with lowest energy.
Sorry.
So E going to this E naught, and that would be you know, something that is, it's looking very similar to, yeah, it's the limit where the wormhole is pinching off, where the bottleneck size is shrinking to 0.
Right. Okay, thank you.
Yeah, curvature is blowing up. And the third question is, can we extract meaningful information away from this kind of singular region of moduli space, if you will. Let me call E like a modulus, pseudomodulus. Can we extract meaningful information away from there? And in short, the answers to all 3 of these questions are in the affirmative. So we know how to uplift the analysis that I just presented in AdS to 1 in 10 dimensions or in 11 dimensions for any of the standard lampposts of AdS CFT. So we know how to uplift. It's kind of easy. The wormholes that you get end up just, you know, they look like, you know, if we're talking about AdS 5 times S5, the 5-dimensional part, the metric is like, there's a wormhole, and then there's a constant size 5 sphere, and there's a Ramon flux that comes along for the ride that's basically fixed by flux conservation. Sorry, by Gauss's law, rather. It's getting late. When it comes to stability, we do not have a proof of that these wormholes are stable. One of the things that we run into is an old problem in Euclidean gravity, that namely what to do with the conformal mode. But I could explain as best we can tell, despite some questions about what to do with the conformal mode, these wormholes do look like they're perturbatively stable configurations of gravity. We have been able to check the most dangerous sectors, at least, of for potential decay channels, potential instabilities, and those seem to be absent. But of course, if we're talking about full AdS CFT, there's more instability channels than just perturbative fluctuations of supergravity fields. There can also be brane nucleation instabilities. And we have analyzed the most obvious nucleation instability channels. And what happens there is a little bit more detail, but the short version is basically there's brane nucleation instabilities for the wormholes I presented, but it depends on where in moduli space you are. But there are wormholes that are macroscopic, but that are relatively small, where this B is order 1, but where the wormhole is still big, you know, it's not pinching off to 0, where those are stable against brane nucleation. So there are complete, yeah. But the last thing is probably the most. Go ahead, Saad.
Suppose we were interested, we were focusing on the dominant one, the one that has lowest action, the pinch off singular guy. If we don't worry about the singularity for a moment, is that configuration also a solution of just plain old Einstein's equations without any of this gauge fixing?
Well, how to say? The thing is, how to say? This B, I said there was the lowest value of 1. I guess the question is whether or not this 1 includes 1 or not. And anything that's away from that's in the interior of moduli space is not a solution. And then at the tip, let me think for just a second. I think in that case, I don't think that's the solution either, if I remember correctly.
You know, I was thinking, it seems sort of intuitively strange to me that you've got a solution of the gauge fixed equations that wasn't a solution of the non-gauge fixed equation. And I was trying to resolve that by saying that there was one direction left, which is your moduli space of solutions. So only the lowest guy.
Yeah. Okay, I think I know how to make sense of your question, Shiraz. The parameter is not the B parameter, it's the boundary inverse temperatures. So when the boundary inverse temperatures sum up to 0, then you have a solution. That can be achieved in one of two ways. That can, either beta 1, beta 2 are real and opposite. And as I mentioned earlier, that's the Euclidean black hole.
Mm-hmm.
That jives with what you're saying. The second possibility, so beta 1 is minus beta 2 equals real. That's the Euclidean black hole. Another possibility is that beta 1 and beta 2 are opposite but pure imaginary.
Mm-hmm.
In which case the geometry is Lorentzian, actually. And in that case, that's an orbifold of the Lorentzian two-sided black hole, where you basically identify real time after some amount, capital T, the size of and that's this double cone of Saad, Shenker, Stanford.
Okay. So is it right in some sense that the reason that you got a new solution, you got a solution when you, in the gauge fix theory, when you didn't get it before gauge fixing, is that the theory without gauge fixing varies with one more direction, which is basically a moduli space of solutions.
Yes, that's exactly right.
Okay, thank you. Then it makes complete sense. Then it's very much like the constrained instant.
Oh, absolutely, absolutely.
Okay.
Yeah, it's like you think of it as foliating field space.
Right. Perfect. Thank you.
Yeah.
Just
okay.
one.
So the third question.
Sorry, Kristan. Just one last thing. Where did this cutoff on B come from again? That B had to go up till 1. It's probably tied to your E being some minimum value. But how did that arise?
Yeah, I mean, so if you stare at this factor here, it's I mean, in the metric that I wrote, it's because you want. Oh, that was the eraser. There's this factor here, which I want to always be bigger than 0.
Okay. Okay.
So it's analogous to in JT, why B is lower bounded by 0. You want for you posit that you should be summing over non-singular metrics.
Right. Okay. Thank you. Go ahead, please.
Yeah. Okay. Sorry, this is going. I'm failing my challenge. I'm almost done. The most interesting, so I said these wormhole amplitudes are UV sensitive, but nevertheless, we can still get some meaningful information from them away from the endpoints. And the way we do it is the following. We can think of the wormhole as a canonical ensemble quantity. It's labeled by beta, right? Mm-hmm. So what we can do is we can look at a microcanonical version where we fix the energy. And for technical reasons, it's convenient to consider a microcanonical version where you introduce a resolution scale, like what we usually do in microcanonical ensemble. So you have a delta in addition to an energy E. And the way you do that is by, how do you go from canonical to microcanonical? Well, you inverse Laplace transform. And if you introduce a resolution scale, then you pass that modifies the integral transform, you pass it through a Gaussian filter as well. So the proper formula here is this. In the inverse transform, the integral transform, you actually integrate over the betas. And you integrate the whole wormhole amplitude. And something I can do before doing that is to shift the betas by a bit, by some imaginary parts. Right, and it turns out, well, if you do this, how to say, if you tentatively identify the wormhole amplitude as contributing to the connected 2-point function of z, then what this integral transform is it's where you look at energies it's close to some energy E within a resolution scale. So that's the thing that you would write. And well, basically, you know, the thing before was a non-saddle in the energy E, but now we integrate over beta 1, beta 2 as well. So we change the problem. And it turns out that this deformed problem where you integrate over energy and beta 1 and beta 2, this admits a saddle point approximation in all three of those quantities.
And then so is also a saddle point without this gauge fixing business?
Exactly. And that saddle point is nothing more than the double cone of Saad, Shenker, Stanford. And so, okay, so you find a known configuration. It's an orbifold of the two-sided black hole. It's a generic configuration. Whenever you have a Lorentzian black hole, you can always get this double cone from it. And you know, one way of summarizing this excursion into Euclidean gravity is to say that, well, I mean, you can really land on that thing from Euclidean gravity. And it also gives, you know, and to some extent, you need to run through all these steps in order to understand the right rules for discussing loop corrections, the one loop determinant around double cone and so on.
So sorry, Kristan, I'm really sorry to be so ignorant, but you know, having sat through many talks, but the double cone again is what you take the double, the thermofield double and make an multiplication after some amount of going forwards in time. Is that what it is? Sorry.
That's right. You take the two black hole exteriors, and then you identify them you identify along that time by some amount t.
I see.
And it's a double cone because you know you how to say this. In this orbifold, you kick out the black hole interior. You're just keeping the exteriors, and the exteriors because you know that you've now identified time. Time is a flat circle. Well, that circle shrinks at the bifurcation point, and the two exteriors meet at the bifurcation.
I see.
Surface.
I see. And so that's
a cone.
You get here as well, huh?
Yeah, these Euclidean wormholes that I got, solutions to this gauge fix thing, in this analytic continuation, how to say, you know, this integral that I just wrote down, there is a saddle point approximation to it, and that saddle point in gravity is exactly it's an analytic continuation of the original wormhole that I wrote down, where beta 1 is IT and beta 2 is minus IT. And that is this, they sum up to 0. So that's the solution to the field equations, as Shiraz keeps mentioning, has to be. And that is this double cone. And why is it the cone as opposed to just the black hole? It's because the time, you know, in the Euclidean place where you started, time was periodic. So that has to be true in this Lorentzian geometry that you get as well.
Okay, I see. Thank you.
And I should say where all of this, you know, there's this the saddle, you can, how to say, what one can get from bulk effective field theory around it is that, including the one loop effects, that this object is some order 1 number times the time t. That's a top in the limit where this time t becomes very long. And this time t, basically, that factor just comes from, if this time circle is becoming very long, then the only degrees of freedom that matter in the bulk are the very light degrees of freedom. And in general, most of the fluctuations here are gapped, except for a zero mode, which is a relative translation of one boundary to the other. And you can time translate one boundary circle relative to the other, and that zero mode has a volume that's going to be proportional to the overall size of the circle. So that's where this factor t comes from. And it's worth emphasizing because this is a ramp in the spectral form factor, in this microcanonical spectral form factor. So that's the sense in which you can get a ramp out of Einstein gravity, supergravity, what have you. And okay, well, the way I structured this talk was to focus on this first. This is a wonderful feature. This is a very, this is something that we should expect from n equals 4, from ABJM, from any complicated many-body Hamiltonian. However, these wormholes come with a problem that we were discussing at the beginning of the talk: breakdown of factorization. So this is, but I wanted to emphasize first maybe that, unlike in the context of the old black hole information paradoxes, where, here, the thing that is introducing a problem, these wormholes, from the point of view of factorization, they're describing something physically very reasonable. To wit, draw this picture one more time. The two boundary problem that we're dealing with, well, we're seeing there's some disconnected contributions. And then there's connected ones. And the thing is that, if we're talking about a consistent theory of quantum gravity with a conformal field theory dual, then, well, in the dual conformal field theory with a single instance, there should be no connected part. And we expect in the two boundary problem that computes, if boundary here is M1 and boundary here is M2, that this is the CFT partition function on M1, CFT partition function on M2, and that factorizes by locality. Or sorry, I should have written union, direct union, and that factorizes by locality. If you put a CFT on something with disjoint boundaries. So there's a breakdown in factorization implied by these wormhole amplitudes. And, at some level, the problem, how to say, it's sharpest in the context of this double cone, I would say. That's the sharpest that one can make the factorization paradox. There's other wormhole solutions that one can find in Einstein gravity and supergravity, but they're usually either unstable or kind of esoteric. There's a wormhole that Maldacena and Miles found when they pointed out this potential problem with factorization. It's a AdS5 times S5 wormhole where you have some instanton number for the SO6 gauge field coupled to n equals 4. You have a non-trivial instanton background for the R symmetry on the two boundaries. And well, anyway, this thing with the double cone and what I've described, this is completely vanilla. This is generic. This is something that, well, okay.
I have a question.
And there doesn't seem, oh, go ahead.
So the disconnected and the connected pieces have same value of the small parameter small b or not?
So the disconnected ones are saddles. They're not labeled by, if we fix, say we're dealing with S1 times S3, then, they're just some function of the inverse temperatures. But the connected one, the way we've worked to be able to write it as some integral over a parameter b. You could take an integral transform of the whole problem, and then b is effectively fixed. This energy is effectively fixed by doing that.
So I thought once we gauge fix the b, b is a fixed number after gauge fixing. B was related to the.
Yeah, B is still, there's a family of these wormholes that we get, and you have to integrate over the family. And then what happens is that, if you want to consider a deformed version of the problem, relevant for not the full spectral form factor, but this microcanonical thing, then that would effectively pin down this modulus B. So that's the connection, but the disconnected geometries don't have a B. Right, so, with regard to factorization, I guess what I would say we have done is to kind of emphasize something that at some level was already anticipated by Juan when he wrote this paper with Maus almost 20 years ago, which is that there doesn't seem to be any obvious reason why these connected contributions should vanish. And I guess the extra ingredient since then is that, if you take these, like maybe the strongest statement is that if you take these integral transforms, you look at microcanonical, blah, 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 then you really get a saddle point solution, this double cone of Saad, Shenker, Stanford, which would which would be in contradiction with factorization of boundary partition functions. So what does this mean, and what does this mean going forward? Well, the story is still developing. It's not at all clear. It's an active topic of research. And I want to emphasize maybe 3 quick points about it before signing off. The first is to say that this is really a problem about non-perturbative physics in the bulk. And usually what we would say in AdS CFT, the last 20 years is that, well, string theory, we don't really understand what its non-perturbative completion is apart from conformal field theory, when there's a dual CFT. Here, these are non-perturbative effects where CFT doesn't help us. So it's not clear what's the way forward, I would say. Saying that, there's one copy of n equals 4 once and for all doesn't help us with figuring out what is the right prescription for developing type 2B string theory on AdS 5 times S5, what topologies we sum over, which ones we don't, what kind of things we include from a 10-dimensional perspective. The second comment is that, I want to give you some kind of sense of what this ensemble averaging that seems to be coming out, what it's doing. These effects in gravity, what they correspond to are some uncertainty in the spectrum of black hole microstates. That seems to be the simplest place where it appears. In particular, the spectrum of unprotected black hole microstates. And I don't know, I think it raises the question whether or not there is some non-perturbative ambiguity in what we mean by string theory, where the spectrum of black hole microstates differs depending on, there's some non-perturbative ambiguity that nails down exactly what is the spectrum of some black hole.
But Kristan, you must complete, because I know it's past midnight for you. But just to say, if you believe AdS CFT, then there shouldn't be any ambiguity, right?
Yeah. So, right. So
So
I do believe in AdS CFT. It's certainly the religious upbringing of my career in physics so far. But I don't know. I think it's important to be led by computations and not by priors. And I think what what the question really boils down to is how it's well. And this is what I was going to say. Well, the reason why I include this second point is to say I don't know of another way of answering this question directly in the bulk. I know an answer in CFT, which is just to assert this does not happen. But I want to see a bulk explanation that for pinning down the spectrum of black hole microstates. And I don't know one at present, and so that leaves me unsatisfied.
Okay, thanks.
Yeah, go ahead. I see a raised hand from Karam again.
Yeah, I can ask this towards the end if you want. I mean, I think you can, I'm just leaving it up for now, and I can ask it towards the end.
Okay, sounds good. Maybe yeah, another way of saying that the second point is that, how to say, if I keep an open mind, I don't know of a reason per se, just purely in the bulk, why such an ambiguity should not exist. If I'm talking about very, very heavy states, non-perturbatively heavy states, and they're unprotected by supersymmetry, then I don't know, and I would like to know. Unfortunately, that seems like a bit, writing it this way, it seems like an impossible question to address within my lifespan, but maybe things will work out better.
Yeah, just to say, I mean, when you say ambiguity in string theory is not even well enough defined to compute such things at the moment, right? So you're
exactly
saying ambiguity in the final completion of string theory.
Yeah, that we don't know yet. Yeah, yes, I completely agree. The third point is that there's a recent idea from the Stanford group, which people are talking about, and which they're really able to develop in the context of, I thought going down to 2D gravity and 0 + 1 dimensions on the boundary was going pretty far. Well, they go even further. They go to 0 + 0 dimensional Grossman integral. So think like a version of SYK at a single time point. And they're basically able to pose and to solve a version of factorization paradox that appears in that setting. And the way they're able to do it is that, if you look at the thing that if you were studying a problem that would be like a 2-point function of partition functions, something that has no connected part in their model, that they're able to reformulate that in terms of some collective fields. And the things that you would think of as being the gravitational variables, the weakly coupled degrees of freedom at large n. And the crucial thing is that if you're very careful, you find that there are extra degrees of freedom than what you would have naively expected. So extra collective fields and description of ZZ. And those correspond to some extra non-perturbative ingredients that you need in order to get ZZ right, to see that there's factorization. And they're able to, in their model, to see all of this and to figure it all out. What I would say is that this is a lovely picture for what might happen for n = 4. But we really, the problem at hand is that our best knowledge of the collective field description of n = 4 is precisely type 2B string theory on AdS 5 times S5. And one needs something that's more fundamental than that to see, maybe the picture sort of in some very moral sense, that there's extra degrees of freedom, there's extra rules that we have to follow in 10 dimensions. Sure, that sounds wonderful to me, but we need to have some more fundamental formulation of string theory than we presently have in order to make progress there. And that was my last point. That's how I wanted to end. My apologies for going so long. I hope this was very fun for you. It was fun for me. Thank you.
So maybe we can thank the speaker.
Kristan, very quickly, thanks for a fantastic talk, and I won't take more time, but just very quickly, there was also this paper from Stanford where they looked at one instantiation of the SYK, right? And then didn't they find this kind of wormhole, but they found extra contributions which would lead in effect to the two boundaries disconnecting.
Yeah, so they have some claims about what happens for SYK as well. I'm a bit more cautious about those claims because what they do, how to say, my understanding of their discussion of SYK is that they have a prescription for basically finding saddle point-like configurations of the two boundary problem. And those configurations include things that they call half wormholes, analogous to what they are actually able to compute in 0 plus 0. The thing is that I find very confusing about their SYK analysis is that this prescription, I don't understand how to talk about loop corrections around it. Basically, the idea is you have some collective field version, two different collective field versions of the two boundary problem. Or sorry, you have some collective field version of the two boundary problem where you find some wormhole-like configurations and some things that they dub linked wormholes, half wormholes. And then the latter is something that they plug into the one boundary problem and then expand around it. The problem is that when you do that, you don't have a saddle, like the thing that you're plugging in is not a saddle of the one boundary problem. It's a saddle of this two boundary problem. So I don't understand what their proposal is at loop level. So I feel, I like the idea, of course. I think it's a great idea. But I would really say that they've only posed and solved the paradox in 0 plus 0.
Okay, thank you.
Can I ask a question, Kristan?
Okay.
Sorry, go ahead.
I just wanted to actually ask about this the status of these connected pieces and whether they're really tied to like a non-perturbative effect. So what I mean by that is, could it be that through loop corrections or higher derivative terms, they could sort of go away in principle, order by order. So like we're extracting this information entirely from Einstein gravity and just considering these possible geometries. But then if you take higher derivative corrections, could it be that these terms just cancel out? These contributions cancel out? I guess that's part one, and part two would be, I mean, I guess this is not appropriate to ask in some sense, but the Turiachi paper that you were referring to with respect to the gravity mean at the boundary, how does the picture change in terms of your results? Like you said, it's generic, it holds across the board for like ABJM and yeah. But like if you do take fermions on the boundary, how do your results qualitatively?
Okay, so the second question is easier to address than, I mean, it's their work, so they'll have to speak for themselves. But the picture is that that they advertise is that if you know what I was discussing was boundary conditions in AdS that are appropriate for looking at thermal partition function on the boundary.
Right.
If instead you look at twisted boundary conditions appropriate for computing the superconformal index, then in that case, there are gravitino zero modes on these wormhole geometries. Basically, the result is that anything that's not BPS, a BPS saddle in the bulk, will have such a zero mode. And the BPS ones do too, except the zero mode is pure gauge. And so, you know, you don't integrate over it. So that the second one is easier to answer. The first question about loop corrections and so on and higher derivative stuff. Well, how to say, if I look at one of these fixed macroscopic wormholes, if I fix the B parameter, if you will, then there's no reason in the loop expansion why I expect loop kill this. Oh, earpiece finally died.
Okay, so it would just get corrected, is what you're saying. Like those parameters would just get corrected at loop level. Hello?
Let's do it. Can you hear me?
Yeah, it's breaking up, I guess. But it could be from my end. I'm not sure.
Okay. Thank you. Okay. So there's no reason, how to say, there's no like ghost zero mode, as I said, that would kill, that's something that could appear in the loop corrections that doesn't. And then when it comes to higher derivative terms, well, if you're dealing with a fixed macroscopic wormhole, then the higher derivative corrections are going to be small in string theory. They're going to be 1/root lambda suppressed.
Okay.
Or alpha primes. Yeah. They're going to be alpha prime suppressed. Now, the crucial statement there was to say if we're at fixed size, if we consider a fixed one of these wormholes, and the only way I know how to do that consistently is by taking this transform relevant, this thing that got the double cone. So we've changed the question that we're answering to this microcanonical spectral form factor, blah, 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 blah. And in that case, the higher derivative corrections one expects to be small.
Okay.
Now it's a little subtle because this double cone, there is this orbifold singularity that one has to deal with. The Stanford group has thought much more about what to do with that orbifold singularity, how to formulate string theory consistently in that background in such a way that it, well, how to say it, you can look at their 2018 paper to see their discussion of it. But the point is that the curvatures there, how to say, you know, like the Riemann curvature there is not blowing up. There's some subtlety with what to make of the time circle shrinking, but curvatures are not blowing up. And so in effective field theory grounds, one expects alpha prime corrections to still be small.
Okay. Thank you.
There's a, yeah.
Can I ask a question, Kristan?
Of course.
Yes. So unfortunately, I could only join about 20 minutes into the talk. So I don't know if you have discussed this point already in the beginning. But one thing that is usually I find not too much discussed in these contexts of these ensemble averages, etc., and the wormholes is the failure of cluster decomposition that such a thing would lead to, and how one addresses that issue. In the, you know, when the correlators are at widely separated, spatially separated points, then one expects the correlation function to factorize into blocks. I mean, factorize into this group and the correlation function of the other group, right? So if you have an ensemble average or some wormhole configurations in the bulk, which would kind of give rise to non-factorization, they would also give rise to some failure of cluster decomposition. So
I would say that's the Lorentzian. I would say that is the, you know, there's a Euclidean problem that wormholes force upon you, which is factorization paradox. And I would say that there's a Lorentzian version of the problem if you continue to real time, and it's what you said, it's cluster decomposition or alternative, like, you know, if you put your operators all the way out on the boundaries, it's that operators on the boundaries do not commute with each other. I did actually say this at some point in the talk.
Okay.
I said it in the context that it's very important that these wormholes are not saddle points, because that would be a very glaring problem in the AdS CFT correspondence if that there were saddle points of Einstein gravity that had that feature.
I see.
But there's no, like, you know, there's no apparent reason at hand why off shell, why the whole amplitude, you know, which, okay, there's no saddle point, but there's a whole sum to still perform, why that should, which would exhibit this problem of, which would lead to a non-perturbative violation of cluster decomposition, why that shouldn't be there.
Okay, I see. So you're saying there is no reason why, you know, the bulk could not compute, not CFT, but some, you know, where not observables where cluster decomposition does hold, but it could compute something where it fails by a little bit.
This is the heart of the question. Yeah, what is the bulk computing exactly, and what is our definition for the bulk?
So from that,
I guess I would just say, yeah, the thing you're mentioning, it's essentially the same problem. It's just in Lorentzian signature instead of Euclidean.
Okay, thank you.
Any more questions?
Hi, I have two questions. One,
assuming Kristan has the energy to answer at this time. Is this okay, Kristan?
You know, I drank an espresso before this, figuring that it would be an interactive talk. So I'm still,
yeah. So please
I'm warm, but I'm still going well. Go ahead.
Yeah, thank you. So, the way we pass on to this gauge fixed action, is it clear that the solution, this double boundary solution, is independent of the gauges we choose, or does it depend on the gauge?
Yes, I mean it's a saddle of, because it's an orbifold of a solution, the Lorentzian black hole. It's it doesn't depend on any of this stuff that I mentioned about the gauge fixing.
And also it is clear that once it for the gauge fixed action, when you have propagating gravitons, they remain massless and so on.
Yes.
Thank you.
Yeah.
Okay, great. Maybe I can ask a very quick, sort of a slightly vague question. Right at the beginning, we were talking about various possible, we were talking about time average as a possible averaging that could give rise to this non-factorization. So I wanted to ask, suppose the rule was just that for this spectral form factor, we have Z at T times Z at minus T, and then you multiply these two things and then time average over some small time averaging window. This would also lead to non-factorization, right? So perhaps that is the rule. Is that a possibility? Has it been explored in detail?
Yeah, that's. I mean, yes. I guess the question is, effectively, could it be that the right dictionary between bulk and boundary quantities involves little in it? I mean, if you wrote that out, that would involve, some integrate. How to say? I mean, if you wrote there would be an integral expression for the object that you just described, right?
Right, an integral over a range that is large, small compared to 1, but large compared to e to the power minus n squared.
Yeah. And the claim would be that when you look at gravity, that there's some kind of hidden resolution scale that we don't see at any order in an expansion over topologies that's sitting there, a resolution scale, and somehow that's what gravity is computing. That could, I mean, I don't know how to rule that out. That's at this time. That would be an alternative dictionary.
Right. And this would go in the direction of your saying that there was ambiguity in gravity.
Yes.
Okay. Fine.
Yeah.
Okay.
It would, in that case, it would be an ambiguity in the dictionary between, what is this computing in CFT?
Yeah, right. But somehow the claim that the bulk is not a very precise thing. It's precise up to a certain place.
Yes. It's not precise enough to address precisely these questions.
Okay, great. Any final questions? Okay, if not, let's thank Kristan for a marathon and fantastic and talk, and one that he stayed awake so long for. So thank you so much.
Thank you. Thanks for being patient with me. I'm sorry it went so long.
No, it was great. Thank you so much.
Thanks so much. Thank you.
Bye.
Bye.
Okay. Well, take care. Hope to see you sometime.
I hope so too.